Welcome back to the deep dive. Today, we're really embarking on a journey into some pretty fundamental mathematics, stuff that lets us, visualize and interact with the invisible forces all around us. We're going to try and bridge the gap from understanding how, say, a simple wire creates magnetic field all the way to the sophisticated mathematical language that describes how any field changes, flows, and swirls in 3 dimensions. Our sources for this deep dive are some really rich texts that delve into Ampere's circuital law and the powerful tools of vector calculus in 3D. Think of it as a shortcut to really grasping how current creates magnetic fields and the advanced mathematical frameworks that underpin our understanding of how things change and flow in space.
Exactly. And our mission here is really to distill the most important insights from these sources. We want to help you grasp these complex ideas with hopefully some clarity, see how they intricately connect, and, gain a unique understanding without getting totally bogged down in the weeds. We'll explore not just what these principles are, but fundamentally why they matter for understanding our physical world.
Okay, so let's start with the foundational concept then. Ampere's circuital law. It's a really profound statement, isn't it, about the relationship between magnetic fields and the electric currents that produce them. What's the core idea here?
Okay. The law states that the line integral of the magnetic field, which we usually write as B around any closed circuit, is equal to a constant mu naught, that's the permeability of free space, times the total current I that passes through that closed circuit.
Right, and when you say line integral around a closed circuit, what does that actually mean physically?
Imagine you have a loop, any closed loop. You go all the way around it, and at each tiny step, you measure the component of the magnetic field that points along your path, and you sum all those up. It's essentially quantifying the sort of circulation of the magnetic field that the current creates around itself.
Okay, so mathematically, that's the EBLU equation.
That's the one. EBELAE equals LLAI. And briefly, the proof, if you like, often involves considering a simple case, like an infinitely long straight wire, and showing the angle between B and your path element DL is 0, which makes the integral easier to solve.
And what's really revolutionary about it, wasn't it that it showed magnetism isn't just there? It's a dynamic consequence of moving charge, a huge step.
Absolutely. A critical insight that paved the way for Maxwell's later unification.
Okay, so this law isn't just theory, it's incredibly practical. Where does it actually get used? How do we see its applications?
Oh, it's fundamental for calculating magnetic fields, especially in situations with some symmetry. For instance, take that infinitely long straight wire carrying a current I. Using Ampere's law, the calculation simplifies beautifully. It gives us the magnetic field B at a distance r from the wire as B equals I divided by 2r. Simple, elegant, and incredibly useful.
Yeah, that formula comes up a lot. It's sort of
Yeah.
the backbone for understanding many electrical components, right?
Definitely.
And beyond just a straight wire, what about more complex shapes?
Well, take solenoids. Picture a long insulated wire wound up in a tight helix shape.
Right, like a coil.
Exactly. When current flows through it, the solenoid behaves remarkably like a bar magnet. The interesting part is the magnetic field inside is surprisingly uniform and strong, while the field outside is incredibly weak, often negligible in calculations.
Okay, uniform inside, weak outside. Is there a formula for that inside field?
Yes. If n is the number of turns per unit length of the solenoid, the magnetic field inside is simply B equals mun I.
Oh, no. Simple enough.
Then you have toroids.
Toroids.
Yeah, imagine taking that long solenoid and bending it into a donut shape, connecting the ends, an endless solenoid in a ring.
Okay. Like a donut-shaped coil.
Precisely. When current flows, the magnetic field gets trapped inside the toroid, running in concentric circles. And again, the field outside the toroid is essentially 0.
And the field inside. Same formula.
Looks the same. Bn is slightly different. It's the total number of turns, let's say n, divided by the circumference of the toroid, which is 2r, so n 2 par.
Okay, so why do we care so much about these specific things, solenoids and toroids?
Well, it raises an important point. We care because they aren't just textbook examples. They are absolutely fundamental components in countless technologies. Think about electromagnets in scrapyards, or the transformers that step voltage up or down, or the inductors in electronic circuits that store magnetic energy. They all rely on these principles. Understanding these field calculations, how strong the field is, where it is crucial for designing and optimizing all that stuff.
Right, without that understanding, we couldn't build or improve the technology that, well, runs our world.
Pretty much.
So, Ampere's law is great for these symmetrical cases. But you mentioned earlier, what if things aren't so neat? What if we want to describe how any field behaves, spreading out, swirling around in any situation? For that, we need a more general language, right? Vector calculus.
That's exactly it. Vector calculus provides the mathematical toolkit for describing fields in 3 dimensions, and the core building block, the sort of central operator, is called del, or nabla. It's written as the symbol church. Think of it as a vector made of partial derivative operators.
Okay, nabla. What can we do with it?
Well, 3 key operations arise from it. Let's start with the gradient, written as arras, nablafy, where it is a scalar function, like temperature or pressure. The gradient, sure, is itself a vector, and this vector tells you 2 crucial things. First, its magnitude, its length, is the maximum rate of change of that scalar function at that point. Second, its direction points precisely along that direction of maximum change.
Hold on, partial derivatives.
Yeah.
Like Urix. Can you quickly remind us what that means?
Sure, arish just means how much the function changes if you only vary the x-coordinate a tiny bit while keeping y and z fixed. It's the rate of change purely in the x direction.
So the gradient combines those rates of change in x, y, and z.
Exactly. The formula is urgis plus izzy plus insk, where I, j, k are the unit vectors in the x, y, z directions.
Okay, let's try that analogy you mentioned earlier. If k is temperature on a map.
Right. Then the gradient vector at any point on the map points in the direction you should walk to get warmest the fastest.
Ah, and the length of the vector tells you how fast the temperature is rising in that direction. The steeper the temperature hill, the longer the vector.
Precisely. It's very intuitive. And its applications go beyond temperature, finding vectors perpendicular to surfaces, finding the direction of maximum change for any scalar field.
Okay, gradient makes sense. What's next?
Next up is the divergence, usually written as div A, or using nabla, it's uyo, nabla.a, where A is now a vector field like fluid flow or an electric field.
Dot product.
Yeah.
Okay, and what does divergence measure?
We define it as the outward flux of the vector field per unit volume. Essentially, it measures how much the vector field is spreading out from a point, acting like a source.
Or converging into a point, like a sink.
Exactly. A positive divergence means it's spreading out, a source. Negative divergence means it's converging, a sink.
Let's use that water analogy.
Yeah.
If AO represents water velocity.
Then at a tap where water is coming out, the divergence would be positive. Water is spreading out from that point.
Okay, and at a drain where water flows in.
Divergence would be negative. Water is converging there. It's a sink.
Simple enough. Does it connect anything deeper?
Oh, absolutely. What's fascinating is its direct link to fundamental physical laws. For example, the equation of continuity in electromagnetism is div j plus r equal 0. Here, j is the current density vector, and r is charge density.
Div j plus euro 0.
This equation is just a mathematical statement of the conservation of charge. It tells us that charge can't just appear or disappear out of nowhere. If the charge density at a point is decreasing, or it is negative, then there must be a net outward flow of current from that point. Div j must be positive. Charge has to flow.
Wow, okay, so divergence is tied right into conservation laws.
Yeah.
Very cool. What's the third operation?
The third one is the curl. Written as curl A, or using nabla, it's ubla across A. Again, A is a vector field.
Cross product this time. Okay, so divergence was about spreading out. What's curl about?
Curl measures the circulation or rotation of a vector field at a point. Think about stirring coffee. The velocity field of the coffee has curl because it's rotating.
Okay, so if a vector field is swirling around a point, it has a non-zero curl there.
That's the idea. If the line integral of the vector field around a tiny closed loop is not 0, the field has curl at that point. We sometimes call such fields non-conservative or non-lamellar. The magnitude of the curl vector tells you the maximum amount of this circulation per unit area, and its direction points along the axis of that rotation, determined by the right-hand rule.
So back to the coffee cup. If I dropped a tiny imaginary paddle wheel in there,
the curl vector would tell you the direction of the axis the paddle wheel would spin around and how fast it would spin.
That really helps visualize it, connecting the math to something tangible.
And physically, the curl is incredibly important. It's crucial for understanding rotational effects. For instance, going back to Ampere's law in its differential form, it actually says that the curl of the magnetic field is proportional to the current density, J.
Well, wait, so curl B relates to J.
Yes,
Yeah.
ignoring time-varying fields for now. It's another way of saying that electric currents cause magnetic fields to circulate or curl around them. It connects directly back to Ampere's law, but now from a more general, local perspective using calculus.
That's a fantastic connection, tying it all together.
Yeah.
And you mentioned conservative fields.
Right. A key point is that if a vector field is conservative, meaning the work done moving between 2 points doesn't depend on the path taken, like an electrostatic field or a gravitational field, its curl is always zero. Change E, zero for electrostatics. No intrinsic rotation.
Okay, so gradient for rate of change, divergence for spreading, converging, curl for rotation. Powerful tools. But you said there's more. How these operators connect through theorems.
Indeed. These individual operators are powerful, but it gets, as you said, even more profound when we see how they're connected by fundamental theorems. These theorems bridge different types of integrals, line, surface, and volume integrals.
Pillars of mathematical physics, you call them.
They really are. They give us amazing flexibility, allowing us to convert integrals from one type to another, often dramatically simplifying problems. Let's start with Gauss's divergence theorem, sometimes just called the divergence theorem. It states that the total outward flux of a vector field A through a closed surface S, remember flux is like the total amount of stuff flowing through the surface.
Okay, flux to a closed surface.
Is equal to the volume integral of the divergence of that vector field, div A or HUA, over the entire volume V enclosed by that surface.
So the formula is AU at diff, AGS, AUA, double integral for surface, triple for volume.
Exactly. AOS of AUS equals over V of div A dV.
Okay, let's try to unpack that. It's like saying, if I want to know the total amount of water flowing out of an imaginary box, the surface integral of the flow, I don't need to measure it everywhere on the surface. I could just measure how much water is being created or destroyed inside the box. By looking at all the little sources and sinks, the divergence inside, and adding them up, the volume integral.
That's a perfect analogy. It connects the behavior on the boundary surface to the behavior within the volume.
That sounds incredibly useful.
It's profoundly important. It leads directly to Gauss's law of electrostatics. That law says the total electric flux through a closed surface is proportional to the total electric charge enclosed within that volume. Using the divergence theorem connects this directly to the divergence of the electric field.
And from there you get other big equations.
Precisely. Combining Gauss's law with the definition of electric potential leads to Poisson's equation, Shark-Sena, which relates the potential to the charge density.
And if there's no charge, 0,
Then you get the famous Laplace's equation, H equals 0. That little edge symbol, the Laplacian, is just dig grid. These equations, Poisson's and Laplace's, are absolutely fundamental. They pop up everywhere. Electrostatics, heat flow, fluid dynamics, gravity. They describe potential fields in countless systems.
Wow. Okay, so Gauss's divergence theorem is huge. What's the next big one?
Next up is Stokes' theorem. This one connects surface integrals and line integrals. It states that the flux of the curl of a vector function A over an open surface S.
Open surface, like a sheet, not a closed box.
Exactly, like a patch or a disk. The flux of the curl of A over that surface S is equal to the line integral of the vector field A itself around the boundary curve C that edges that surface.
Okay, so the formula is A curl A. Surface integral of the curl equals the line integral around the edge.
That's it. A over S of AAS equals A over C of A a day.
What's the intuition here? Gauss connected volume to surface via divergence. Stokes connects.
Stokes connects the swirliness or rotation of the field across the surface, measured by the curl, to the total circulation of the field just along the edge of that surface, the line integral.
So if I want to know how much the field is generally swirling across a whole area, I just need to walk around the perimeter and see how much the field pushes me along.
In essence, yes. It's incredibly elegant. It tells you that the accumulated microscopic rotations, curl, inside the surface add up to produce the macroscopic circulation around the boundary.
That sounds really powerful for simplifying things again.
It is. It's fundamental to understanding things like electromagnetic induction. Faraday's law of induction in integral form is basically Stokes' theorem applied to the electric field induced by a changing magnetic field. The changing magnetic flux through the surface, related to the curl, equals the induced voltage or electromotive force around the loop, the line integral of E.
Amazing how these concepts interlock. Is there another major theorem? You mentioned Green's theorem.
Yes, Green's theorem. There are a couple of forms. One relates a line integral around a closed curve in a plane to a double integral over the area enclosed. But the one often discussed alongside Gauss and Stokes in 3D is sometimes called Green's second identity or theorem.
Okay, what does that one do?
It relates volume and surface integrals involving scalar functions and psi and their Laplacians. It requires these functions to have continuous second-order derivatives. The formula looks a bit more complex. Fitchushi, Sudi, Sushu.
Whoa, okay. That one's less immediately obvious than the others, perhaps.
It is perhaps less intuitive at first glance, but it's derived directly from Gauss's divergence theorem by applying it cleverly to combinations of scalar fields and their gradients. Its real power comes in solving certain types of partial differential equations, particularly in potential theory, wave propagation, and even quantum mechanics. It allows you to relate the values of a function and its derivatives inside a volume to values on its boundary surface, which is extremely useful in mathematical physics.
So it's another tool for transforming integrals, maybe for more advanced problems?
Exactly. A powerful tool in the mathematical physicist's arsenal derived from the more fundamental divergence theorem.
Okay, so let's try to bring this all together. What does this journey mean for our understanding? We started with Ampere's law, specific rule, current makes magnetic fields circulate. Then we zoomed out to this language of vector calculus gradient, divergence, curl, giving us the words to describe how any field changes, spreads, or rotates in 3D space.
Right. And if we connect this to the bigger picture, these concepts, these operators, these theorems, Gauss, Stokes, Green, they aren't just abstract math. They are quite literally the bedrock of classical physics. They form the language we use to describe electromagnetism, fluid dynamics, heat transfer, even aspects of gravity. They allow us to take complex physical phenomena and translate them into equations we can actually solve.
And solving those equations leads to, well, everything.
Pretty much. From designing antennas and motors, to predicting weather patterns, to developing medical imaging like MRI, which relies heavily on controlling magnetic fields. It all comes back to understanding and applying these mathematical descriptions of fields.
So through this deep dive, you've hopefully seen how a magnetic field can be described, how we can quantify rates of change, gradient, spreading, divergence, and rotation curl, and how these incredibly powerful theorems, like Gauss's and Stokes, link everything together, connecting behavior inside a region to what happens on its boundary. It really feels like a shortcut to being genuinely well-informed about how the physical world operates at a fundamental level.
Absolutely. It's the framework that underpins so much, which perhaps raises an important question for you, the listener, to think about. How might a deeper understanding of these fundamental mathematical descriptions of fields, how they change, interact, and propagate, allow us to, perhaps, predict, control, or maybe even engineer entirely new physical phenomena, things we haven't even discovered yet?
What new technologies or insights might emerge if we gain an even deeper command of these forces and the mathematics that describes them?
Exactly. What possibilities open up?
A fantastic thought to ponder indeed. We hope this deep dive has sparked your curiosity and maybe given you a clearer lens through which to view the forces shaping our universe. Until next time, keep exploring, keep questioning, and keep diving deep.